I'm super thankful to be here today. Thanks to Jeremy for organizing this session. I'm going to be talking about switching from kind of a theoretical perspective to more of an empirical perspective to try to see if we can test how environment-dependent reciprocal benefits are in kind of classic mutualism. So first, I'd like to thank my co-conspirators on this, Peter Tippin and Brendan Epstein, who's done a there that really, without which none of this would have happened. I'd also like to thank NSF's PGRP for funding this. So I'm going to talk about the coolest of organisms and mutualisms. You passed by them, I'm sure, on your walk-in today. Clovers, but then there's also legumes and rhizobia or legumes that are invasive, legumes that are pioneer species, and also legumes that are fundamental to agriculture, right? Like peanuts and, well, not the most important, but soybean and lentils. And in all of these cases, they have this mutualistic relationship with rhizobia. In general, the net benefits, we call it mutualism because the net benefits of this relationship outweigh the costs. And in this particular case, the bacteria provide the nitrogen to the plant. They're taking atmospheric nitrogen and converting it into a plant-usable form, essentially fertilizing the plants. And the plant is actually providing carbon and benefits from the photosynthesis to increase the fitness of these microbes. It's all happening in this super cool organ called a nodule, where they're living in symbiosis in really close proximity to each other. And I'm going to argue, like Justine did earlier. First I'm going to say that I think it's fundamentally important for us to understand how these sorts of relationships are going to change in response to environmental changes. And in the case of this mutualism, I think it's particularly important to understand it because this mutualism is at the crux of the nitrogen and carbon cycles. Microbes like rhizobia are the only, well, the primary natural source of plant-usable nitrogen. And we also know that the nitrogen, the primary aspects of this relationship are changing, right? So nitrogen deposition from fertilizer is increasing, and carbon dioxide is increasing here. So how do those environmental shifts alter the outcomes of this relationship? And also more indirect environmental factors like temperature and moisture. And how is that going to influence the evolution of this mutualism and thus related to the downstream outcomes of this mutualism? Wow, this is right. Okay, so I'm going to argue that this is not a new question, but that it's really one that's been hard to study. And we've spent a lot of time measuring how plants and the benefits that plants receive from these microbes might shift with environmental factors. But we spent a lot less time actually explicitly measuring the benefits that the microbes are receiving from this relationship and how that might change with environmental factors. And that's what I'm going to do today. But the reason that we haven't done this isn't because it hasn't been of interest, it's because it's really hard to do. So if you step back to the ecologically complex environments that these organisms live in, these bacteria are living tons of strains together in the soil. There's a lot of them. And when a plant starts growing, very few of those strains are going to actually make it into these nodules, into association with these plants. Right? So a plant maybe forms 10 to 100 nodules, and only about one strain is going to actually make it into each of those. So this is a massive bottleneck. And then, once this plant has formed these associations, different nodules can have different strains in them. And once they form, now these nodules can grow to different sizes. So the rhizobia not only wants to get into the plant, it also wants to be in those nodules on that plant that release the most bacteria back into the soil. And this is the biggest benefit of this relationship from the microbial perspective. So what we really want to measure is we want to know how many of each of these different strains are being released into the soil at the end of this competitive relationship. But it's hard to keep track of strains in soil and natural environments, and so most of what we know about this direction of this mutualism comes from measuring these relationships in single-strain environments using things like nodule phenotypes as proxies for fitness. So in this case, we're missing this competitive part of the process. We're missing competitive part of the process here. And it's really hard to grow all these time, we're only measuring the outcomes of these relationships in one environment when we're doing these experiments. So what I did for my postdoc was to develop methods to try to get at this question mark, so we can start to manipulate the environment and see how these relationships are changing. The experimental system I'm going to use is metacognition catch-all, related to alfalfa. It's a genetic model, and its mutualist is Insular mallotai. You may know this is rhizobia. And there's many cool things about the system, but one thing that's particularly important to me is that metacognitive nodules are super duper selective. So if you actually sample the soil, the rhizosphere nodules, and use 16S sequencing to see who's in each of those environments and divide it up into different phyla, you can see that in the soil there's a ton of different phyla, bacterophyla, but by the time we get to the nodule, they're primarily proteobacteria. And what's super cool is these plants are only letting in this one genus of proteobacteria into these nodules. And I'm going to argue that if we want to understand the evolution of these strains, we can't use these 16S sequences because 16S sequence is identical. So what I did was develop a method to basically measure, in this fraction, who's winning and losing in these competitive interactions. So what I did was basically develop an evolving sequence method that basically, importantly, the first step is to actually sequence all of these different rhizobia strands. And this basically gives us a barcode or a fingerprint of SNPs, 128,000 of them, that we can use to identify these strains after selection. I grow them all up in a mixture in culture, and then expose, and so they're approximately proportion in this mixture, and then you expose them to whatever environmental selective treatment you want, whether that be these host plants, like I've been talking about before, but these bacteria also live in the soil, and they're also used in culture environments. So you can use whatever environment you want, and then you basically sequence, use whole genome sequencing of that selected pool of strains, and there's cool maximum likelihood methods you can use to reconstruct strain frequencies from that whole genome pool of sequencing data. So I've done this before, and this is published, but here's kind of what you get when you run this experiment. So here's our initial community of 68 strains. If you inoculate plant hosts, allow those bacteria to compete, form nodules to be different sizes, take that set of nodules, crush them up, see who's inside. Here's two different host genotypes. So you can see this red strain is at higher frequency in these nodules, in this whole pool, this is a whole plant level, than this other genotype. And we can use methods like redundancy analysis to basically look at, to summarize these shifts, complex shifts in strain frequency you see in different environments. So here each dot is a different replicate, and summarizing, and dots that are closer together have more similar strain communities, or strain fitness, and dots that are further apart have more different. In the course of doing these experiments, we really wanted to check if this competitive metric of mixed strain fitness was different from those single strain experiments that are generally done. And so we grew each of these strains individually with each host, and we found that there's no correlation between what is assessed in single strain and multi-strain environments. This is a very different set of traits that we're measuring here in the single strain inferences of fitness. But what's cool about having that single strain data is it allows us to go one step further and ask about the fitness alignment between these two sets of organisms. So on the x-axis here, I'm showing you bacterial relative fitness. So this is just a transformed frequency, essentially, where any dot here, so each of these is a strain, any dot that's above zero is a strain that's increasing in the nodules, and any dot that's down here is basically a loser or decreasing. And on the y-axis, I'm showing you plant biomass. So in that single strain experiment, how big did a plant grow when it was inoculated? And the key take home here is that this one host genotype is pretty good at associating with helpful strains. But this R108 genotype is actually pretty bad. So there are plenty of strains that are high frequency in the nodules that are actually providing very little benefit. So the experiment I want to show you today is basically asking how and if these relationships change when you subject them to environmental perturbations. And so I'm going to put this in the context of understanding the relative importance of these host genotypic differences and these environmental differences. And the treatments I'm going to use are in addition to those two host genotypes, I have a nitrogen addition treatment. So remember, this is basically adding the resource that the bacteria is providing to the plant. The hypothesis here is that if you add nitrogen, maybe the plants are less selective and less dependent on this bacteria. This is a fairly weak nitrogen addition treatment. The second treatment is a bacterial density manipulation, where I put 100 times more bacteria onto some of these plants than the others. And the idea here is that if there's less bacteria, the importance of competition between these strains might be weaker. And we have no idea how population sizes are going to change with climate change. Okay, so I did 6 replicate pots of each of these different treatments. For the rest of the top, red are high density treatments and blue are low density treatments. So what did I find? Here is that same redundancy graph we saw before, where each dot is a replicate pot. And the first thing to take away from this is this first axis of variation explains the vast majority of the variance. So really pay attention to differences along this axis. The second thing is this is a redundancy analysis that allowed an interactive effect of host density and nitrogen. So host has a massive effect. So all of these are R108 and all of these are A17. So regardless of these environmental perturbations, we're getting consistent differences in strain frequencies in these nodules. And you can see that in the statistics as well. The second take home is that density had a far bigger effect on strain fitness than the nitrogen effect. And this is the opposite of what I thought would happen. And there's an interaction between host and density where the R108 host changes its strain fitness in a different way than the Okay, so let's get back to that question then, the key question of, are these shifts in strain fitness that we observe, are they actually shifting the beneficialness of this community? And I'm basically summarizing those graphs you saw before with this metric, which is basically predicted reciprocal benefit. It's a frequency-weighted mean of that biomass that we observed before. And so here, you can see, basically a 1 would mean that every strain that came out of those nodules is the most helpful strain possible. So A17 is still more helpful than R108. But, and this we see in other metrics like biomass and different, very different nodule phenotypes and things like that. But the really cool thing, I think, is that density actually had a huge effect on the beneficialness of this community, and it happened in opposite ways in A17 and in R108. And in both cases, basically when you reduce the number of bacteria they had to associate with, nodules were less nodules, but the ones that were formed were larger. But A17 is getting less helpful and R108 is getting more. So what do I make of all this? This is all brand new unpublished data, but I think that it means that these host genotypes are really consistent mediators of strain fitness and these reciprocal benefits. So let's keep studying host genetic variation. Let's study what's happening in these different agricultural species and in natural species and really try to understand how these reciprocal benefits might be changing with these environmental factors. Secondly, this nitrogen addition didn't actually alter the plant or strain benefits, but it did affect the plant phenotypes. And so there seems to be a lot of conflicting evidence about this. So let's try to nail down the effect of all this fertilizing we're doing on the outcome of these relationships. And lastly, I think this density effects need to be looked at. Oh, wow, okay. Sorry. Okay, thank you.